In this episode of Home Theater Geeks, I talk about a new technology for sound absorption and acoustic treatment in rooms and other enclosed spaces. This one gets pretty geeky, so stay tuned.
Podcasts you love.
From people you trust.
This is TWiT.
This show is brought to you by members like you. Thanks.
Hey there, Scott Wilkinson here, the Home Theater Geek. Among the many newsletters and news items I get on a daily basis by email is a newsletter from an outlet called New Atlas. And they talk about all kinds of interesting technologies and so on. One story in one day a few weeks ago really caught my attention. It was about something that they called plasma-based active noise cancellation. And I thought, that's pretty interesting. So I clicked through, and what I found was really interesting, and I thought I'd share it with you. Now, most audio buffs know about active noise cancellation in headphones, sometimes called ANC. So you're wearing these headphones or earbuds. They have little microphones built in, and there's ambient noise outside. I use these all the time on airplanes because there's a lot of ambient noise in an airplane, low rumbling sound from the engines. So these microphones in the headphones pick up this ambient noise, send it to a processor, which reproduces that waveform 180 degrees out of phase with the incident sound that's coming in. And then it plays that phase inverted version of the ambient noise in the headphone speaker. That combines with the actual sound itself, and they cancel each other out. If you remember anything about high school physics, you might remember phase cancellation. So if you have one sound and they have another sound that's the same but 180 degrees out of phase, mix them together, they cancel each other out, and the result is nothing, zero. Well, in ANC headphones, it's not quite zero because the processing isn't perfect, but it reduces the sound greatly. Then the music that you're listening to is also played on the headphones, but that doesn't go through that processor, so you hear it just fine. So the question is, what if you could do that in an entire room or other large enclosed space like a car or an airplane? Now, such a system wouldn't be able to cancel certain sounds and not others like the headphone does because it's isolated. But it could provide acoustic treatment. Instead of using big, bulky panels and bass traps and stuff that people use in their home theaters right now to tame certain frequencies that are too loud and try to even things out and make the sound better. Now, you could use an array of speakers to do this. You could just put a big array of speakers on the wall and use the same kind of processing that they use in headphones to create a counter wave, if you will, an out-of-phase version of whatever the microphone hears, and that would prevent sounds from reflecting off the wall. But that would still be big and bulky and expensive and heavy because you've got a whole array of speakers that you have to drive somehow. Lots of amplification. It would be a lot. So this article talked about another solution to doing this. It came from a Swiss laboratory called EPFL, École Polytechnique Fédérale de Lausanne. And they had a different idea, which is now being developed in conjunction or in partnership with a company called Sonexos, another Swiss-based company, which is an engineering firm. So instead of having an array of speaker diaphragms vibrating out of phase with the incoming sound wave, the EPFL idea is to take a thin layer of air and ionize it and cause it to vibrate with an oscillating electromagnetic field. Whoa, hang on there. That's a lot going on right there. So I want to explain ionization first. So if we take a look at graphic number 2, I believe. That's right, graphic number 2. This sort of explains ionization. So matter is including air, gases, solids, liquids, all are made of atoms. And the atoms are primarily electrically neutral. They're the same number of protons, which are positive, and electrons, which are negative. But if you supply enough energy into the field where the atom is, it can knock one of the electrons out of orbit, and it becomes a free electron. And then the atom is no longer neutral, electrically neutral. It has a net positive charge because there are more protons than there are electrons. And the free electron is floating around and it has a negative charge. So this process is called ionization because the atom becomes what's called an ion. An ion is a particle, an atom or an electron that's free by itself, and it has an electrical charge, either positive or negative. So, and an ionized gas, that is a gas that in which the atoms have been ionized, have a charge, is called a plasma. That's in fact the fourth state of matter. Remember I mentioned gas, liquid, and solid. Those are the three basic states of matter that we all learn about in high school physics. But there's a fourth state called plasma. And that's what happens when you ionize the atoms in a gas. It becomes a plasma. And EPFL realized that if you ionized a layer of air, it would become a plasma, and you could do things, which I'm going to explain what you can do to basically counteract reflections, prevent reflections. They call this thin layer of ionized air or ionized plasma a plasmacoustic metalayer. Man, I love how they come up with these names. So they built a little device that includes a conductive mesh and some nichrome wires. That's graphic number 3. And here we see a little prototype. It's small. They've made larger ones since. But you see this mesh, which is conductive, and you got a wire attached to it. And then you can see in the background behind, in that little cavity, some thin wires. Those are nichrome wires. And those are electrified as well with the other cable. So inside the device, inside that cavity, there's a thin layer of air. And when they apply a certain type of electrical voltage to those two ends, the air ionizes. The electric field inside that chamber causes some electrons to scoot out of the atoms in the air, and they become ions, and the gas becomes a plasma. Then what they do is they apply an oscillating electromagnetic field into that chamber, and those charged particles, the ions, start to vibrate in response. In fact, the response is virtually instantaneous. Unlike a speaker diaphragm, which has a lot of mass, and you apply an alternating current to it, and it starts to vibrate, and it gets going, and it starts vibrating. But since it has a lot of mass, it takes a while for it to get going. This air, the molecules, the atoms have virtually no mass. I mean, they do have mass, but it's very small compared to a diaphragm. And they start vibrating virtually instantaneously. And so depending on what kind of oscillating electromagnetic field you apply, these ions start vibrating. They bump up against others, and they bump up against others, and they finally bump up against the neutral air atoms and molecules that are next to this device. And a pressure wave starts expanding and propagating out into the world, and you get sound. Now, this concept can actually be used as a speaker, and it has been in the past. A number of companies have come up with what are called plasma tweeters. They're mostly used in the high frequencies. In fact, EPFL has a little video on their website, which we'll include in the liner notes, rather the show notes, from the New Atlas article. There's a video in there that demonstrates this technology being used as a speaker. And it doesn't do very well in the low frequencies as a speaker. The fidelity isn't that great. So, it's if you use it as a tweeter, there are high-end companies that do that, and it's interesting. But this article and this company is more interested in using the effect for other things. So I've got some graphics from the scientific paper that I was led to from the New Atlas article, and I've included that link in the show notes too, but beware, there's some serious math going on in there and some serious scientific depth. So don't worry if you don't understand it. I'm going to explain a couple of the graphics here for you. So graphic number 4 gives us a basic idea of how it works. So here we see the little device with the mesh at one end and the nichrome wires on the other end. The mesh is called the collector. The nichrome wires are called the emitter. And there's a rigid wall behind it, as you saw. Basically forms a cavity. Okay, so a wave comes in. That's the green wave that you see in A here, the section labeled A on the left side of the diagram. The whole ionization thing is just turned off. It's just not working at all. So the sound wave comes in, it reflects off the wall in the back of the chamber and heads out, right? So you can see that at the bottom. The green wave is the wave coming in, it reflects off the rigid wall, and the blue wave is the reflection as it goes out. Okay, now we turn on the plasma system, which ionizes the air in this little chamber, and then an oscillating magnetic field, electromagnetic field is applied to vibrate the ions, the plus ions, here in this lower part of the right-hand diagram, are the atoms with an electron removed. They vibrate back and forth. They bump into neutral air molecules and cause a sound wave to go out the other way. Now, a processor causes that sound wave to be 180 degrees out of phase with what came in. And so what the wave that is reflected, you can see in the top of the right-hand part of this diagram, the blue wave has very much less amplitude. It's very low amplitude, so there's not much coming out of it. It's not being reflected, which is the point. Now, graphic 5 illustrates an experimental setup and some results, and I wanted to show you that too. So in the upper left, you can see here's the sound source. It's a little speaker being powered by a power amplifier. It's sending sound waves down this tube to the meta layer, what's called the meta layer, which is EPFL's nomenclature for the ionized layer of air. You can see here a little picture of the thing itself, grounded mesh, nichrome wire. It's 50 millimeters wide. This is a little test thing. The analyzer analyzes the sound coming out of the speaker. The controller controls how the metal layer is being ionized and vibrated. And the result you can see down here in the lower part of the diagram, when the plasma acoustic metal layer is active, the absorption coefficient is very flat. It absorbs almost everything from 20 hertz up to 2 kilohertz, 2,000 hertz. This was the experimental area that they were looking at. When they turn the ionization off, making a passive plasma acoustic metal layer, that is, there's no plasma there at all, the dotted red line near the bottom is the absorption coefficient, which is basically wasn't absorbing anything. It was reflecting everything. So this is very effective over a wide range of frequencies. They also show here, just for comparison, there's this solid blue line, which is a porous sound absorbing material. And you can see it does no absorption below 100 hertz. And it slowly starts creeping up at 100 hertz, 200 hertz a little bit, and 400. And by the time it gets to 1,000 hertz, it's absorbing a lot. But it's obviously not uniform across a wide range of frequencies. They also tried it with a resonator. And as you would expect with a resonator that resonates at a certain frequency, it absorbed only in a very narrow range of frequencies, in this case around 300 hertz. So that demonstrates how effective it is at doing sound absorption, which is really what they're talking about. And it doesn't mean that it's absorbing the sound. It means it's preventing reflections, or that it's canceling reflections is a more accurate way to say it, because the sound coming in is being phase canceled. The reflection of it is being phase canceled completely. Now, graphic 6 shows a few different interesting applications. So in these graphs, I'm not going to explain all of them, but the graph in the upper left shows how they were able to affect the amount of absorption or of cancellation. So they were able to, in the blue line at the top, they were able to do a 0.9 absorption, which is a lot of absorption. Most of the sound did not get reflected back out. The red line is 0.7, so some of the sound got reflected back out, but not all of it. In fact, most of it didn't. And the green line is a 0.4 reflection, so more of it got reflected out. And in the lower part of the left-hand side of this diagram, you can see that the phase of the reflection didn't change over, in this case, 50 hertz to 1,000 or 1 kilohertz. So this, I'm looking mostly at the left side of this diagram to show that the amount of absorption or amount of cancellation can be controlled. And this is really important. This brings us to how this might be used in a home theater. So the primary application, as I've said, is sound absorption. If you were to try to put some absorption in your home theater or any room that would absorb 20 hertz, that is the lowest frequency that we humans can hear, it has a wavelength of 56 feet. And to effectively absorb it, you would need sound absorbing material about 13 feet thick. And I doubt there are many places where you'd be able to make a 13-foot thick wall with sound absorbing material. It's very, shall we say, impractical. The plasma acoustic system can do it with a device less than 1 inch thick. That's amazing. And their experiments in the first case went from 20 hertz to 2000 hertz, and they were very uniform in the amount of cancellation that they could do. And because the amount of reflection or absorption or cancellation, if you will, is tunable, the possibilities for home theater are almost endless. You don't really want a room in which all the sound is absorbed and never reflected back. That's called an anechoic chamber. And if you've ever been in an anechoic chamber, you know it feels really weird. That is not what you want in a home theater. You want some reflection, but not too much. And you want a certain amount from different parts of the room. In particular, you want less coming from the areas of what are called first reflection. So the speakers in the front send sound out in a wide pattern typically, and they reflect off the walls. And you want more absorption in the place where that sound first reflects off the wall. And you want less in other places in the room. So if you could have these panels and set them in different places in the room and tune them to how much they reflected, that would be huge. That would be amazing. Now, there's also the issue of reducing noise levels in cars and planes. As I talked about before, we wouldn't need noise canceling headphones if the interior of a plane or a car were coated with this kind of technology. And how about in a restaurant? Ever been in a restaurant where the clattering of dishes and the chattering of the people are all over the place, and the walls are cement or glass? I mean, that gets intolerable. Cover the walls with this plasma acoustic technology, and it would be a much more pleasant environment. But we home theater geeks like to think about home theaters, and I think this would be amazing technology to deploy in a home theater. It's not a viable commercial product yet. You can't go out and buy it. But I thought it was so interesting to look at the future of what home theater and other acoustic treatment might be headed. It's really quite something. So I hope you found it as interesting as I did. It's pretty geeky, and you can get more information in the links that we've included in the show notes, including the technical paper. So if you've got a degree in physics, you'll get something out of that paper. If not, I'd suggest reading the other two, which are more for general audiences. So there you go. As we always love to answer listener questions on the show, so do hope you will send them to htg@twit.tv, and I'll answer as many of them as I can. I'm starting to get more and more, so there's more stuff to talk about here on Home Theater Geeks. And as always, we thank you for your membership in Club TWiT, which supports the entire TWiT network, as well as this particular show, Home Theater Geeks. With that membership, you can come into the Club Discord and watch us make the show live, so I hope you will join us. Until next time, geek out.